recording. All right, so this is Math 150, Calc 3, multivariable calculus, lecture 17. So it's the 16th and 17th, so fix that. Okay. So what I want to do today is talk a little bit about directional derivatives, and then use the rest of the time to really talk about some of the key objects we've been looking at. And so, for instance, I don't think we've talked about how do you take the derivative of, say, x to the square root of 2. More importantly, I don't think we've even talked about what does x to the square root of 2 mean. And so one of the purposes of this class is to get you to a point where you at least understand where you have to be careful in mathematics so that you understand what you manipulate. It is very easy to just manipulate, and not really understand what you're doing. If there's time, I'll talk a little bit about Lagrange multipliers, which is one of the next important units we're going to be discussing. It's one of the first real applications of calculus. It's one of the things that we're doing that's going to make a real difference in solving problems. So again, who are my economists or people in econ classes? So hopefully you'll be seeing Lagrange multipliers in terms of solving some systems of equations. For the most part, the amount of calculus you need to do in any of these problems is really negligible. It's a very small amount of calculus to set up the problem. And then it's a lot of algebra to just work through and solve it, if you're lucky enough to be in a situation where you can solve it. Most of the time, you can't solve it. So most of the time, you have to resort to numerical methods. All right, so the first item is directional derivatives. So as a rule of thumb, always start with something you know. So let's go down to one dimension. Can somebody tell me what is the difference between a directional derivative in one dimension and a derivative in one dimension?
The derivative is not the overall function.
No, I mean one dimension now. The difference in one dimension between the derivative and the directional derivative. There is none, right? You're not going to see any real difference when you're confined to live in a line. So in a line, the derivative and the directional derivative are the same. When you're in several variables, you have an opportunity of working in 3-dimensional space, 4-dimensional space, 5-dimensional space. You have more ways to walk, you have more ways to move. And the question is, how much am I changing if I move in a certain direction? So the partial derivatives tell us how much we're moving in special directions. The partial derivatives are directional derivatives. So we've actually seen these before. So partial derivatives are examples. And they tell you how fast the function is changing along directions parallel to the coordinate axis. You want to consider the more general case. And so what you could do is you could say, here is some curve, and at a given moment in time, here is C prime of t. And this is my curve C of t. So I'm traveling on a curve. At some instant, I'm moving in the direction of C prime of t. And I want to know maybe how fast is my function changing in that direction? Why would I want to do something like this? Well, if I look at, say, A of t is f of g of t, this is a function of one variable. We know how to calculate derivatives of functions of one variable. This is just A prime of t. But using the chain rule, this is going to be the gradient of f at g of t, right? Oh, I'm sorry, I'm not using g of t, I'm using c of t. Dotted with c prime of t. So this is what we get when we look at the chain rule. And if we want to expand it out, it's partial f, partial x1 at the point c of t times dx1 dt at t plus partial f, partial x2 at c of t times dx2 dt at t plus dot, 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 and so on and so on. And you can see the dot product now coming from the chain rule. The first component is the gradient of f. The second component is c prime of t, where c of t is just x1 of t dot 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 xn of t. So c prime of t is just x1 prime of t dot 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 xn prime of t. Okay. So if I can parameterize how I'm walking in space, I've got some curve c of t, and I look at f of c of t. This is now a function of one variable. I know how to take derivatives of functions of one variable. Always go back to what you know. Well, what would the derivative of a prime of t be? Well, it's just the gradient of f dotted with c prime of t. Well, c prime of t, that's the direction I'm moving. And so this is basically giving me the rate of change in the direction I'm moving. And so the more general, we'll look at the directional derivative at v of f at a point P is just going to be the gradient of f at P dotted with v. And we'll often choose the length of v to equal 1. So there are many ways to compute the directional derivative. The least favorite is to go back to the definition of the derivative. And this is done in notes. You look at the limit of p plus tv. You're moving a little bit in the direction of the minus f of p divided by t times the length of v. So you could do something like that, and you'll see this emerging. Or you can imagine we're walking along some path c of t. And at that moment over here, c prime of t, the tangent to the curve, is the instantaneous direction we're going. And when we look at the derivative, we see it's just the gradient of f dotted with c prime of t. So what this means is, if I know the partial derivatives, if I know these special directional derivatives, I can get any directional derivative. What might be a really good choice for c prime of t? What might be a really good choice for your vector v? What might be a good directional derivative to try to find? So I claim this n very natural choices for this problem, for how you should choose your vector, your direction. I'm not asking for greatest. I'm asking which would be the good directions to test. We want to always just. Yeah, so if I take the standard directions, well, we already know we get the partial derivatives. The directional derivative along the x1 axis should be the same as df dx1. The directional derivative along the x2 axis should be the same as df dx2. So if we take, c of t to basically be, we take v to equal our direction ek, then the directional derivative in the direction of ek of my function at the point P would just be the gradient of f at P dotted with ek. Well, that's just going to be df dxk at P, because ek has a 1 in the kth slot and 0 everywhere else. So this tells us that if we take the directional derivative in one of the standard n directions, we regain the partial derivatives. This is a good consistency check. The directional derivative collapses to the partial derivative when we go along the coordinate axis, or parallel to the coordinate axis. It just generalizes this and now allows us to look at how a function is changing in any direction. And the best way to think about this is, if we just imagine a curve, we've reduced the function to a function of one variable. Have I mentioned the law of the hammer yet this semester? Does anybody know the law of the hammer? if all you have is a hammer, pretty soon every problem looks like a hammer. There's lots of different formulations of this. There's a lot of ways to look at this. One way is whatever somebody asks you to do, convert it to a problem that involves a hammer if you're really good at using a hammer. How many of you have ever watched a presidential debate? How many of you have ever listened to the response of a candidate to a question on a presidential debate? After about 30 seconds, how much of the answer relates to what the question was and how much of it relates to whatever they wanted to talk about? You use the opening to move to whatever you wanted to say. If you're really good at using a hammer, whatever I give you, you try to find a way to use a hammer on it. That's one way to view the law of the hammer. There's a more active way to view the law of the hammer. And the more active way is go to the land of the screwdriver. If they could have solved the problem using a screwdriver, they would have. They're smart people. If they haven't solved it yet, they don't have the right tools. If you have a different tool set than other people, you have a greater chance of making a real contribution. I've written papers in accounting, marketing, economics, computer science, geophysics, the list goes on and on and on. And I can often convert these problems to number theory or combinatorics, and I have a different skill set in these problems than the people who are working on these problems in those fields do. You do not want to go head to head against Gauss in mathematics. We have a few additional things, but Gauss was smart. What do we have that they didn't have back then? You need to find out what is your competitive advantage. And so this is one of the things that's wonderful about being at a school like Williams, a liberal arts college. You should be taking things across the spectrum. If you come here and only do math classes, that is a mistake. By senior year, of course, you should realize that that's what you want to do. But at least in your first few years, you should be exploring, seeing what's out there and making connections. Because later in life, you say, wait a minute, this reminds me of, well, I have tools from this discipline that could be applied very fruitfully. So always be thinking about the law of the hammer when we're doing stuff like this. All right. Now we get to why do we care about directional derivatives? So it'd always be ever important, who cares? So the directional derivative at b of f at p is our formula, gradient of f at p dotted with v. So when we go back to one dimension, how do we tell where we have a candidate for a maximum or minimum? How do we tell where we have a candidate for the maximum or minimum? Like we're in one dimension. How do we tell where we have a candidate for the maximum or the minimum? How do we find our candidates? The derivative is 0, right? So if we are in one dimension, we want to find where is the derivative equal to 0, right? And so is it hard to find the derivative of function? So tell me where my derivative is 0. Is that where I was traveling? Forget. Endpoints. Never forget endpoints again. Right? It is not enough to just check for where the function's derivative is 0 to find candidates. Right? Why? Okay, so I really could hear you over the noise. That's borderline lie. But it was an excuse to at least allow me to close the door. Due to COVID policy, I will immediately open the door. All right, so we have learned that it is not enough to look at just where the critical points are. We have to check endpoints. And so there are two candidates. So candidates for max and min is derivative is 0, and then the endpoints. When we want to generalize this to several variables, well, the derivative is 0. How do you think this generalizes? So what do you think the generalization of the derivative is 0 becomes? Yeah, all the partial derivatives are 0. Or equivalently, that the directional derivative is 0 in any direction. Because if you're at a critical point, if you're at a local max or minimum, then no matter what direction I choose to travel, I can't be getting larger if it's a maximum, I can't be getting smaller if it's a minimum. I need to be as a function of one variable now. And this goes back to, I can now regard myself as living on a curve. I now have a function of one variable. So all the directional derivatives are 0. The endpoints becomes more complicated because now for the endpoints, you actually have potentially infinitely many points to check. Were there that many points to check here? Does it really hurt to check 2 points? You try running into the door. It's really not that bad. It's not that time consuming to check 2 boundary points, right? To check infinitely many points can be hard. So what if I give you an ellipse? So say 2 minus 2, 3 minus 3. And I want to check all the boundary points. On the inside, to find my candidates for maximum minimum, I'll look for where the partial derivatives are 0. For the boundary, however, I have infinitely many points. Now, in this case, if I'm clever, I know I can write my curve as 3 cosine of t, 2 sine of t, as x of t, y of t. And then we get x of t over 3 squared plus y of t over 2 squared equals 1, which is the equation of an ellipse. So if I'm lucky and I give you a surface like an ellipse, its boundary I can write down in closed form. Hey, its boundary is now a function of one variable. I can take my function f. I can write it as a function f of x of t, y of t, which is really just regarding it now as a function of t on the boundary. And I can now use one-dimensional calculus tricks. And I now look for where is this as a function of t, where does those derivatives vanish? And what's nice is because t can just keep cycling around, there's actually no endpoints to check. So in this special case, we could actually survive without learning multivariable calculus. It would be a little bit more work, but we could handle the infinitely many points. The problem is you start getting into higher and higher dimensions and have worse and worse regions to look at, it's going to become a real nightmare. And so we need a better way. And so it turns out that Lagrange multipliers is the way to go. And that's what we're going to be learning later in the semester. That's, I think, the next lecture is how do we handle all of these points on the boundary at the same time. And again, the goal is not to find the points, but to winnow the set of candidates. So if you only have a couple of things to try, it's not a big deal. You can then just try them all. Infinitely many is going to be time consuming. 5, 6, I can do 5 to 6. Okay, any questions on what we've done so far? So this is the theory of directional derivatives. Again, what's really lurking on in the background is that this is just generalizing the derivative in one dimension, where there's no difference between the directional derivative and the derivative, because you can only move in one direction. And the way we look at things in several variables is we say, well, let's imagine we're on some curve C of t. And as soon as we're on some curve C of t, we now have a one-dimensional object. It's floating in space. So it's weaving in and out, say, in three-dimensional space, but it's really just a one-dimensional curve. And so I can view it as a function of that one variable t. And because it's a function of that one variable t, all of my results from one-dimensional calculus are applicable. So this is the big idea. Go back to what you know, the hammer principle. I know how to do things in Calc 1. Whatever problem you give me, I will reduce to it. All right. Exponential function. So this requires you to go back to your Algebra 2 days. How many of you remember the definition of the exponential function? So there are a lot of gaps in people's background, and it's to be expected. Unfortunately, most of the time, the gaps just stay there. This is one of the few times we actually have a course where we've allotted time to try to fix and say, okay, here's something you should have seen, but probably didn't. And here's something you know, but you may not know why it's true. How many have seen the compound interest definition of the exponential function? So one definition is, imagine interest rate of X per year, compound n times a year. How much is $1 worth in a year? So if n equals 1, how much is $1 worth a year later? If the interest rate is X%. So you have $1, let's say X is really generous, say it's 50%, let's say X is 0.5. How much money would you have after 1 year? 150. So how would I write that in terms of 1 and X? So $1 goes to plus 4 X. You start, one goes to, you start with the $1, and then how much do you gain in interest? We get X for every $1. So how much do we get if we start off with $1? X. So we just have 1 plus X. Now let's take n equals 2. So first, after half a year, they give you half the interest. So they would give you X over 2. So to go to 1 plus X over 2. And now we have 1 plus X over $2. We get X halves interest on that. So I could write it as how much we had, 1 plus X over 2, plus 1 plus X over 2 times the interest, which is X halves. Right? The amount you had, the 1 plus X over 2, well, this is the same as just 1 plus X over 2 squared. When I was an undergraduate, the used book exchange was staffed by humanities students. And the way they did it is they added up how much money your books came to, and they wrote that down on a piece of paper. Then they multiplied by 0.05 or 0.06, whatever the Connecticut sales tax was. And then they added back the amount that they wrote on paper. So as a mathematician, what do you think I told them to do? So they wrote down how much money it was. Let's say it came to $100. They would write $100 on a piece of paper. They would multiply by the sales tax 0.06. So that's $6. Then they would add back the 100 and say, okay, your bill is 106. What did I tell them you could do instead? Yeah, multiply by 1.06. And so they started checking to see if this actually would work. And I said, yeah, I'm willing to give this to you for, well, not for free, but for like 0.01% of all transactions. Sadly, they shouldn't have just given it to them first. That's exactly what we're doing here, right? We take the principal and then we add the principal times the interest. That's just the same as multiplying by 1 plus X over 2. This is just 1 plus X over 2 times 1 plus X over 2. What if we did n times? Then 1 would go to 1 plus X over n to the n. As n goes to infinity, it's called compounded. Anybody remember the word? Continuously. And we have 1 plus X over n to the n. The limit as n goes to infinity is just e to the x. So in particular, if you take x equals 1, you get e. So this is one definition of e to the x. Has anybody seen this definition of e to the x before? Nobody has seen the compound interest definition of e to the x. The only bad thing about not being masked now is I have to remember to hide my emotions. Okay, so you haven't seen the compound interest definition. Have you seen this definition? E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 is the sum, n goes from 0 to infinity, of x to the n over n factorial. How many of you have seen this definition? How many of you have seen neither definition in your classes? So you basically see the Moses from Mount Sinai. There's a calculator and has this button that says E or EXP, and you push it, and it gives you the exponential. Okay. That is an absolutely perfectly fine and valid way to teach mathematics. There's absolutely nothing wrong by teaching people that the way you do these calculations is you just hit buttons on the calculator. It's an excellent way to show people how to do things. Got to worry about the eyes and the eyes showing. So the problem with this, for those of you who saw this definition, when you saw this definition, what class were you taking at the time? Pre-calc. So had you seen derivatives? So you haven't talked about series convergence, you haven't talked about anything like that. And then the question is just, does this make sense? What is e to the x times e to the y? E to the x plus y. Why is that the answer? So why is e to the x times e to the y e to the x plus y? Why? What is e to the x? E to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. E to the y is the sum, n goes from 0 to infinity, of y to the m over m factorial. And let's say e to the x plus y is the sum, k goes from 0 to infinity, of x plus y to the k over k factorial. You've just told me that the definition of e to the x is this infinite sum. Okay, if that's your definition, well, why is the product of two infinite sums the third infinite sum? It's true, but you need to prove this. And this is an incredibly important result. So anybody have a class where they prove this? So we need to prove why this is true. So let's look at what we have over here. So do you agree that when we multiply everything out, every term is going to have x to some power and y to some power? Let's collect all of the terms that have the power of x plus the power of y equals k. So I could collect all the terms where the power is 1, all the terms where the power is 7, all the terms where the power is 0, the sum of the powers. So I'm going to sum k goes from 0 to infinity, and I'll sum L goes from 0 to k, because if the sum of the powers is k, the smallest x can be is 0, the largest power x can have is k. And if I have L powers of x, how many powers of y do I have? The sum of the powers has to be k. If I have L powers of x, how many powers of y do I have? So sum of the powers is k. I've got L powers of x. How many powers of y do I need so that the sum of the x powers plus the sum of the y powers? Well, that would give me 2 L powers. I want to have k powers. So if k equals 10 and L equals 2, I want to get 10 total. I have 2 from x. How many do I need from y? 8. So if I have L from x, and I want to get k total, how many do I need from y? K minus L. So I would have a y to the k minus L over k minus L factorial. Now, so much of math is about pattern recognition. I have L factorial, k minus L factorial. Does that remind you of any expression you've seen in mathematics? You know, any quantity that involves a denominator with an L factorial, k minus L factorial. Yeah, combination. Which combination would have L factorial, k minus L in the denominator? K choose L. So this looks a lot like K choose L. What is preventing it from being K choose L? What do we need to make it K choose L? We need a K factorial in the numerator. Am I allowed to just multiply by K factorial? No. But if I divide by K factorial at the same time, it's okay. And now that I've done this, this is just going to be the sum. K goes from 0 to infinity. I can pull the K factorial outside of the L sum because there's no L dependence. And now I'll have a sum. L goes from 0 to K. K factorial over L factorial, K minus L factorial is just K choose L. And I'll get K choose L, X to the L, Y to the K minus L. But what is that quantity equal to? We've done this earlier when we did Pascal's triangle. This is the binomial theorem. And this just equals x plus y to what power? To the k. And so now, when we see this, we just get it's a sum. K goes from 0 to infinity of x plus y to the k over k factorial, which is e to the x plus y. So the exponential of x times the exponential of y really is the exponential of x plus y. But you have to go through and you have to prove it. It involves switching the some summations around, and you have to show that this converges. You have to do a little bit of work to show that it converges. I'm not going to bother doing that. You have to use the binomial theorem. You have to multiply by 1 in a clever way. Now, what we would like is to interpret e to the x. Let's say x is 2 and y is 3. We would like to interpret this as e times e times e times e times e. But if it doesn't have that interpretation, this is bad. All right. So let's go back to e to the x is 1 plus x squared over 2 factorial is the sum of x to the n over n factorial. N goes from 0 to infinity. Imagine you can take the derivative term by term. So we'll assume the derivative of the sum is the sum of the derivatives. Then this would be the sum, n goes from 0 to infinity of n x to the n minus 1. I'm going to write n factorial as n times n minus 1 factorial. And actually, I'm going to have my sum start not at 0, but I'm going to have the sum start at 1. And the reason is when I take the n equals 0 term, the constant term, what's the derivative of a constant? What's the derivative of 1? 0. So that term doesn't survive. I don't want to deal with 0 over 0. So I'm going to start my sum at 1. Oh, well, this is then just the same as the sum. N goes from 1 to infinity of x to the n minus 1 over n minus 1 factorial. Let's let m be n minus 1. As n goes from 1 to infinity, m is going to go from 0 to infinity. And we get that the derivative of e to the x is just the sum. M goes from 0 to infinity, x to the m over m factorial, which is e to the x. So if we use this as our definition of the exponential function, we get very easily that the derivative of e to the x is just e to the x. Any questions about this so far? There's one thing I've done that should bother you a little bit. We start off with the compound interest definition of e to the x, and then we did the series expansion of e to the x. There's a question you should be asking. So what should you be asking about these two formulas for e to the x? Yes, they're a way to prove that they're equivalent. So hopefully, so let's look at 1 plus x over n to the n. This is going to be the sum, k goes from 0 to n of, I'll write it as n choose k, 1 to the k, we'll do it this way. No, I'll do it this way. And then x over n to the n minus k. So the first term is going to just be n choose 0. The next term is going to be n choose 1, x over n. The next term is going to be n choose 2, x over n squared. Then n choose 3, x over n cubed, all the way down to n choose n, x over n to the n. N choose 0 is what? What is n choose 0? Oh, sorry, it's not n. I have n objects. How many ways are there to choose no objects from n? 1. Now I do n choose 1. I have n objects. I want to choose 1 from n. How many ways are there to do that? N. So I get n times x over n. Now the next one is n choose 2. What is n choose 2? So it's n factorial over 2 factorial n minus 2 factorial. Well, because I have an n minus 2 factorial downstairs, it's just going to be n times n minus 1 over 2 factorial. I'm going to write this as x squared over n times n. The next one is n minus 1, n minus 2 over 3 factorial, x times x, well, I'm sorry, I'll write it as x cubed over n times n times n, and so on and so on. All right. So as n goes to infinity, what does n times x over n go to? It goes to x. Now for the next one, we have n minus 1 over 2 factorial times n times n. N over n times n minus 1 over n times n. What does that go to? As n gets very, very large, n times n minus 1 over n times n. What does that go to? I'm sorry? Why would it go? Why do you think it goes to 0? But the numerator is also getting bigger. The numerator is n times n minus 1. So do we agree that we can cancel out one of the n's in the top and the bottom? Right? Now we have n minus 1 over n. What does n minus 1 over n go to as it gets really large? 1. 999 over 1,000. A billion over a billion and 1. A quadrillion over a quadrillion and 1. So the next term is just going to go to x squared over 2 factorial. For the next term, we have n minus 1, n minus 2 over n. Well, n over n cancels. N minus 1 over n goes to 1. N minus 2 over n goes to 1. That's going to go to x cubed over 3 factorial. We need to do a little bit more work to make this reverse. I'm only doing this up to n. I have n terms, but I'm taking the limit. You've got to be careful. This is not a real analysis course. I understand that. But given that some of you have had instruction where your introduction to the exponential function is that there's a button on the calculator that you can push, and if you give it, I want you to at least see a little bit of where the exponential function comes from, as this is one of the most important functions in all of mathematics. This gives you some idea of the equivalence between the two. So, equivalent definitions. I'm not going to cover it, but I have put over here an advanced slide. You can talk about exponentiating matrices. And when you exponentiate matrices and seen matrices, the order in which you multiply matters, and e to the x times e to the y is not e to the x plus y if you are exponentiating matrices. This becomes extremely important in physics. And again, I'm happy to talk if anybody really cares. I don't want to go into too much detail. Right. So I want 3 calculus problems. I want the derivative of x cubed, I want the derivative of x to the 3 halves, and I want the derivative of x to the root 2. Anybody want to give me the derivative of x cubed? Three x squared. Right? X to the 3 halves. Its derivative. Three halves x to the 1 half, and you want to go for the clean sweep. What's the derivative of x to the root 2? Root 2 x to the root 2 minus 1. And you're using x to the r is r x to the r minus 1. It's about the best I can do. How many of you have seen this rule in calculus? If you have not seen this in a calculus task, I can kind of accept they haven't talked about the exponential function, but we've got to talk about the derivative of x to the r. This is the basic building block. How many of you have seen a proof of this power rule in your calculus class? The derivative of x to the r is r x to the r minus 1. A lot of times it's actually proved incorrectly, because it's only proved when the exponent is an integer. So for x cubed, I would have the limit as h goes to 0 of x plus h cubed minus x cubed over h. This is the limit as h goes to 0, x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed over h. I'm using the binomial theorem. The x cubes cancel, and this is the limit as h goes to 0 of 3x squared plus 3xh plus h squared times h over h. Every term that's left has an h that I can pull out. I've got an h in the denominator. Those cancel, and this is the limit as h goes to 0 of 3x squared plus 3xh plus h squared. Well, what's that limit as h goes to 0? The second and third pieces go to 0, and we just get 3x squared. And we're basically using the binomial theorem for positive integer n. That's the reason why we can prove this. Okay? Let's look at x to the 3 halves. We need to calculate the limit as h goes to 0 of x plus h to the 3 halves minus x to the 3 halves over h. The problem is we can't expand the denominator. We can't expand the x plus h to the 3 halves. We only have the binomial theorem if you have an integer exponent. How many of you have seen a proof of x to the 3 halves in your calculus class? But you all knew its derivative was 3 halves. Like, did the teacher even mention the fact that the proof you got does not work? So this is one of my fears, is that people learn parts of math without learning all the conditions. You have to know what are the conditions on the theorem before you use it. There are 2 ways to prove this. One way, at least for this choice of exponent, is to be extremely clever. Instead of 3 halves, I'd rather have cubes, right? Can you think of anything that you could multiply the numerator by and get, say, the difference of cubes? Excellent. Over x plus h to the 3 halves plus x to the 3 halves. So we've just multiplied by 1. And if we do that, this is now the limit as h goes to 0 of x plus h cubed minus x cubed over h times 1 over x plus h to the 3 halves plus x to the 3 halves. As h goes to 0, this is going to go to 1 over 2x to the 3 halves. Because as h goes to 0, each term is going to go to like x to the 3 halves. We agree on that? And what is this going to go to over here as h goes to 0? X plus h cubed minus x cubed over h. What will that go to as h goes to 0? Yeah, it's almost like this lecture was prepared in advance because we just calculated it, right? So we can just put in the 3x squared, and then we multiply them. So you get 3 halves. X squared divided by x to the 3 halves is x to the 1 half. So if we're clever and we multiply by 1, this is one way we can do the problem. The other way you can do the problem is, let's say we have f of x is x to the 3 halves. Set g of x equal f of x squared is x cubed. G prime of x, now you can either use the product rule or the power rule, is just going to be 2 f of x, f prime of x is 3x squared. So f prime of x is 3 halves x squared over f of x. So f prime of x is 3 halves, f of x is x to the 3 halves, x squared divided by x to the 3 halves is just x to the 1 half. This is the nicer way of doing it. This works for all exponents. All right, we have one slide left. We have one function left. This is going to work out perfectly. X to the root 2. And so this gives me a chance to review, what do we know? This is the hammer principle. We know the exponential function. So let's write x to the root 2 as e to the g of x. I want to find g of x. What should I do to both sides to solve for g of x? What do I do to both sides? Take the natural log. So if I look at the natural log, and we always use log sadly in college for natural log of x to the root 2, it's the natural log of e to the g of x. Now I use my log rules. And this is going to just be g of x times the natural log of e. What's the natural log of e? That's just 1. And this is just root 2 natural log of x. So g of x is just root 2 log x. So this means x to the root 2 is just e to the root 2 log of x is the sum and goes from 0 to infinity of root 2 log of x to the n over n factorial. I'm no longer taking anything to an irrational power. I'm only taking things to integer powers. That's the advantage of the exponential function. I just sum integer powers. Now, if I want to take the derivative of x to the root 2, it's the chain rule. So by the chain rule, it's going to be e to the root 2 log of x times the derivative of root 2 log x. Chain rule, the derivative of a of b of x is just a prime at b of x times b prime of x. Okay, e to the root 2 log x, that's just x to the root 2. What's the derivative of root 2 log x? So what's the derivative of root 2 log x? The root 2 natural log x. Root 2 over x, root 2 times 1 over x. And lo and behold, it's root 2 x to the root 2 minus 1. Where is the minus 1 coming from? It's actually coming from the derivative of the natural log. All right, we did it. It's not even 1050. All right, if you fixed some gaps, saw applications of directional derivatives. All right, this is a good place to stop. Have a good rest of the day.